Let's continue with our analysis of linear continuous time systems. Last time we went over the response of the system to initial conditioning. We assumed that the system is not excited by external inputs. It just had some energy at time t0, which we then used to calculate its response for t greater than 0. What we need to start talking about today is what happens when the inputs are non-zero. And since the system is linear, these two are separable. Our response to initial conditions is separable from the response to the inputs, right? So we can kind of treat them separately, and then at the end add those together to get the total response. I think what I'm going to talk about first is response of the system to a special input function. Remember, our goal is to determine the response to any function, x of t. But right now, we're going to look at a special function. We're going to assume that our x of t is delta of t. If that is assumed, in other words, if I assume that my input is just an impulse, the response of the system to that input we call impulse response. So I guess the title is Impulse Response of Linear Time Invariant System, right? So here's the settings. We have a system. We have input x of t, which we're going to assume is delta of t. And our output y of t is going to be something that we're going to call age of t. This age of t is referred to as impulse response. For obvious reasons, because your excitation is impulse, so the way how the system behaves is impulse response. The system is characterized with a differential equation. So since this is a continuous, that says q of d time operating on y of t is equal to p of d times x of t, where these p and q are appropriate polynomials of a differentiating operator. This is a shorthand notation that we use. In a long form, this is essentially dn plus a1 dn minus 1 plus and so on plus an. Operating on your output, y of t, is going to be equal to b0 dn plus b1 dn minus 1 plus and so on plus bn operating on input. In general case, I guess in most practical cases, order of P of D is equal to M is smaller or equal than order of Q of D, which is equal to N. In other words, this polynomial on the left-hand side is of the higher order than the polynomial on the right-hand side. This is one of the this is common occurrence in pretty much all systems because it kind of leads into stability. You will see that the systems for which this order of this one is larger than the order of this one are generally unstable. And what our goal is, or what most of the systems that we work with would typically have the order of this one larger or at most equal to the order of D of D. So that's what we are. What is the prime concern of our analysis here. Now, before we go into heavy math, or not so heavy, but messy math, right? Let's think about what is actually happening here. The system is relaxed, right? Therefore, its energy stored is 0, its input is 0, its output is 0. So for t equal from minus infinity to 0 minus, everything is 0. Now, something happened at 0, and this is this delta. Remember, delta is of infinitely small duration. It only exists at one point, t equal to 0. And then for t0 plus, there are no inputs, right? So if I were to observe this system for 0 plus on, this system would behave as a zero input system that has some initial conditions, right? So what this delta does, it actually, you can think of it as changing the initial conditions for the system in an instant of time, right? Nothing happens before 0. In 0, this lightning strikes and all of the initial conditions are changed. And then after that, the system is behaving as if it was a zero input system with some sort of initial conditions. This is what is happening. So now, you think about the consequences of that. If I were to observe t greater than 0, this system is behaving as if it were a zero input system with initial conditions. Therefore, what is the shape of this x of t? It has to consist of characteristic modes, right? Remember last time we saw that if you have a system that has only initial conditions, then it is built out of these exponentials e to the lambda t, or we had the format of these functions that are characteristic modes of this particular system. So our impulse response is going to have, is going to be built out of characteristic modes, the same characteristic modes that we observed in the case of a zero input response. Now, the only question that is open now is, what does it look at t equal to 0 exactly, right? What happens at t equal to 0? And then if this polynomial here is of the same order as this one, then what that means is that there is a direct path from input to the output. So that means there is an impulse of the output as well, right? So based on these considerations, I can write a general form of an impulse response. Of the impulse response. And it's going to be something like this. H of t is going to be some constant a0 times delta of t plus characteristic modes. This is how impulse response has to look like. There is no other way, because after t equals 0, as I said, it behaves as the system behaves as if it were a zero input system with initial conditions, so it will have only characteristic modes. And at 0, the most it can have is an impulse coupled from input to the output. Right? So if I now substitute essentially this into this equation here, I can write something like this: d to the n plus a1, d to the n minus 1, plus and so on, plus a to the n, operating on a0 delta of t plus characteristic modes is going to be equal to b0 d to the n plus b1 d to the n minus 1 plus dn operating on a delta of t. Now, if you now expand the top part, you have essentially, let me put a0 here, d to the n plus a1 d to the n minus 1 plus and so on, an delta of t plus d to the n plus a1 d to the n minus 1 plus and so on plus an operating on these characteristic modes. And then that has to be equal to B0, d to the n, plus B1, d to the n minus 1, plus and so on, plus Bn operating on delta of t. Now, let me ask you this. What is this? Remember, characteristic modes, they satisfy characteristic equation. Characteristic equation is the differential equation Q of lambda or Q of d equals 0, right? So this whole thing goes to 0, right? Because they satisfy characteristic equation. So this is what we have here. So this whole thing goes to 0. And if I compare now this and this, it is easy to see that this A0 constant that we didn't know what it is in the beginning has to be equal to B0. So based on this, I can refine my age of t. My age of t has to be of the form beta V0 delta of t plus characteristic modes. That's the format of your impulse response. Now the question is, how do I find out? Remember, characteristic modes are always given to a constant, right? If e to the lambda t is a mode, any constant c e to the lambda t is also a mode, right? These constants need to be determined somehow. So how do we determine these constants? Well, I'm going to first go to an example. There's a method that's called impulse matching that we're going to talk about today. I'm going to first go through an example and talk about how you can do that in this example, and then we'll come up with a generalized approach and a recipe how this is done in the general case. So let's take a look at an example. This is the same as your example 2.3 in your textbook. So here's the system. D squared plus 5d plus 6 y of t is equal to d plus 1 x of t. So this is my, obviously, q of d, and this is your p of d. Okay? And the question is, find out the impulse response of this system. Now, what is the n in this case? N is equal to 2. N is equal to 1. Therefore, n is smaller than, n is smaller than n. Since V0 is equal to 0, there is no impulse in age of t. Right? Age of t does not have an impulse at point t equal to 0. It does not have an impulse, but it has a discontinuity. Right? So, in other words, what I'm saying is age of t. Let's just look at it again. This is t. This is age of t. There are two scenarios. When n is equal to n, then at this point t equal to 0, age of t is infinite, right? And this happens when n is equal to n. When n is larger than n, then age of t does not go to infinity when t is equal to 0, but it reaches some finite value. So let's say it goes like this. There is this discontinuity here, where age of t jumps to some value, but then later on, if the system behaves as if it had initial conditions, and then it relaxes to its 0 input, 0 energy state. So now, the first step is, okay, what is the general form of age of t? It will have characteristic modes. What are the characteristic modes? Let's find them. We know how to do it. So in step 1, find the characteristics mode. And we do that, we say Q of lambda is equal to 0. Q of lambda, in this case, is lambda squared plus 5 lambda plus 6 has to be equal to 0. And here we can easily write lambda plus 2, lambda plus 3 is equal to 0, or lambda 1 is equal to minus 2, lambda 2 is equal to minus 3. So our h of t has a format that is c1 e to the minus 2t plus c2 e to the minus 3t, and then we can put times u of t to indicate that it only exists for t greater or equal to 0, right? It starts. You have these functions exist forever, but we have to say this impulse response exists only for positive t. And the elegant way to say that is you can put this u of t at the end of t to indicate that. Now, so that's the first thing we know. The second thing we know, if I substitute delta of t here, and I substitute, of course, h of t instead of y of t, then I have something like this. I can say h double dot of t, right, just putting h of t here and running the operator, plus 5 h single dot of t plus 6 h of t is equal to delta prime of t plus delta of t. This equation needs to be satisfied, right? Just putting a delta for x and putting h for y. Now, since my h of t looks like this, what I know is that h of t does not have any impulses, but h dot of t does. So h dot of t is going to have an impulse at time 0. Why does it have an impulse? Because take a derivative of this. H of t, when you take the derivative of it, it will actually go to 0, from 0 to some constant value. There's a discontinuity there. So derivative of a jump here is going to be delta function, because it actually changed from 0 to some value. Let's call this k1 in an instant, in no time, right? So there is a discontinuity, there's a delta function in the derivative. And since there's a delta function in the derivative, if I take the double derivative of t, this is going to be k1 delta of t plus some k2 delta of t. Why is there a k2 delta of t? Because before t equals 0, the second derivative was 0. After t equals 0, second derivative has a value. Therefore, there's a discontinuity in second derivative. And for that matter, discontinuity in all the derivatives. So all the derivatives are going to be all the 4 k1 delta n minus 1 plus k2 delta n minus 2 all the way to k n delta of t. Okay? So now, if I substitute this into this and this into this, I end up with an equation that, and then equate term by term, then I will end up with something that is like this. K1 for h double derivative, delta dot of t plus k2 delta of t plus this 5 h dot of, so 5 times k1 delta of t has to be equal to delta of t plus delta of t. And now if I do term by term comparison, if I look at the coefficients with delta, well, actually with delta prime, I get that K1 has to be equal to 1, and then K2 plus 5 needs to be equal to 1 as well. So I get that K1 is equal to 1, and K2 plus 5 is equal to 1. So from here, K2 is going to be minus 4. What is it that we did here? Well, we actually solved for initial conditions. Now that I know what K1 and K2 are, then I can really write what the values of initial conditions are. H of t equals 0 is going to be equal to K1, and H dot of t equals 0. This is what do I have? Value of is derivative of that is equal to K2, so it's going to be to minus, which is equal to 1, and this is equal to K2, which is equal to minus 4. But also, I know that h of t is going to be C1 e to the minus 3, was it 2t or 3t? Minus 2t, and then plus C2 e to the minus 3t times u of t. So here it is. If you see these three together, I have the form of my impulse response, and I have two initial conditions that give me the values for my impulse response at t equals 0 and for my derivative of the impulse response at t equals 0. So now if I put h of t equals 0, this is equal to C1 plus C2, and this is equal to 1. H prime at t equal to 0. Derivative of this is minus 2C1 minus 3C2 is equal to minus 4. And I can easily solve this, where C1 is equal to minus 1, and C2 is equal to 2. So therefore, h of t is equal to minus e to the minus 2t plus 2 e to the minus 3t times u of t. Okay, so that's what's called impulse matching. Now the problem with this is there's a lot of, statements like one knows this, one knows that, right? So it becomes very clear when you come back at my stage and look at it. But when you are trying to build, not knowing what you need to expect, it's difficult to kind of keep track of what you're doing. Just to summarize, and then we'll move on. You actually write your differential equation, and then you determine in the first step the format of your impulse response. And then you really are trying to determine what your initial conditions are. In your initial conditions, you determine some tricks here. You say, okay, well, I know h of t is discontinuous. Therefore, let's call the value that it takes at t equals 0 k1. Therefore, your h prime needs to be that h double prime is derivative of this plus some additional impulse because double prime changed value and so on. You plug it back into the equation and you solve term by term. And then once you get initial conditions and general shape of your impulse response, then by substituting t equals 0, you get the value for this general coefficient. Now, that's I guess, relatively quick and dirty way. More systematic way is, I don't know why the author moved it at the end of the chapter, thinking that maybe you guys are going to get scared of math. But we're going to actually derive it. And what you will see is it will give us a very straightforward recipe of how you determine an impulse response for the system for which you know the differential equation. It's actually, once you go through derivation, you will understand it's a very straightforward application. So determining the impulse response for the system that has no differential equation is a very straightforward process. So let's figure out how to do it. So I guess here, impulse matching method. And this is kind of like a general case. You will see, so far I have restricted myself, to, I guess, based on this example, n smaller than n. This case here will allow us to treat pretty much anything, even the cases where n is larger than n. Right? So we're not going to put any of these restrictions. I'm going to put some guards so that what I do in this example is valid. So here's general settings. I have my system. It has x of t coming into the system, and it responds with y of t in general case. The differential equation is q of d operating on y of t is the same as p of d operating on x of t. This is my system S. For this system, I'm going to attach a companion. And companion system, I'm going to call this S0. This is x of t into that S0. And the output is going to be omega of t. This system is going to have the same q of d operating on w of t, but is going to have x of t here. So in other words, p of d is going to be equal to 1. Okay? Now, the thing here to remember, it is q of d that generally carries the character of the linear system, right? Because the fact that you're differentiating these inputs on the right-hand side is essentially just changing your input, right? You can think of this system here as having a q of d operating on y of t, but being presented with a different input here. Let me call this x prime of t, which is generated from the original input by taking over this derivative. So the system characteristics are captured in this q of d. And for that matter, these two systems are quite similar. The only difference is we're talking about different excitation that they're having. I'm calling this x of t here generically, but this system would behave exactly like this one if I pre-process the input by taking all of these derivatives, right? So here's what the process here is going to be. I'm going to determine the impulse response for this system, right? That's going to be my first step. And then I'm going to try to express the impulse response of this system as a function of the impulse response of this one and this polynomial p of t. Okay? So our first task is determine the impulse. Let me call this companion. The author doesn't call it that way, but I'm introducing this term so that when I reference it, you kind of know exactly what I'm talking about. So first, let's determine the impulse response of a companion system. Okay? So here's what we are considering. We're saying q of d operating on yn of t, where yn of t is the impulse response of the companion system, is equal to delta of t. So in other words, d to the n plus a1 d to the n minus 1 plus n minus 1 plus and so on plus an operating on yn of t is equal to delta of t. Now, since and I can expand this here, and I can say something like this. This is yn of t take an nth derivative plus a1 yn and minus first derivative plus and so on plus an yn of t is going to be equal to delta of t. Okay? Now, let me just put here for the sake of simplicity where y of n of t is essentially d y of t nth derivative over dt to the n. And we'll actually put here n here. Right, so just for clarity of the notation, this y to the n is the nth derivative of yn. Now, let's think about what does this equation tells me. There's a delta on the right-hand side. Which term contains this delta? Which term on the left-hand side contains this delta? Right? If, let's, for the sake of argument, assume that this one has a delta inside. Then the term before is the first derivative. Right? That will have the delta derivative. Then the next one will have a double derivative of delta. None of that exists on the right-hand side. So you cannot make that unless you make all of these coefficients equal to 0. So what happens is, if you look at this, well, from here, the only way that this could work is that the initial, the yn of t and all of its derivative except 1 are equal to 0. And essentially, this equation here has to have these initial conditions. Yn of 0, yn first derivative of 0, and so on, up to all yn minus 1 of 0, all have to be equal to 0. Why? Because if they're not, let's say there is a discontinuity here, and let's say, no, n minus 2, sorry. And yn minus 2, 0 is the different than 0. Then when I take the derivative of this one, yn minus 1 will have a delta, and then y of n will have delta prime, right? And delta prime does not exist on the right-hand side. Therefore, all of these at 0 have to be equal to 0, and then yn minus 1 at 0 has to be equal to exactly 1, right? Why? Because when I take the derivative of this one, I get this guy, and this will be the delta that will, you know, balance the delta on the right-hand side. Okay? So, so now I have differential equation, which is this one, and then I have initial conditions, right? That will allow me to solve the impulse response for this system. I know, just like any other system, the impulse response here will be made out of characteristic modes. Since P of D is equal to 1, therefore B0 is equal to 0, there are only characteristic modes here. There are no delta pulses in the impulse response. And I have a differential equation, and then I have initial conditions that this impulse response needs to satisfy. So it is extremely easy for me to solve the impulse response of the companion system, right? So let me just summarize what I just said. So therefore, yn of t, which is an impulse response of the companion system, is the zero input response with initial conditions given by this equation, or these two equations. These two equations give initial conditions for yn of t. So now, so that's the first part of the problem, right? I am able, I take my original system, I define its companion, and through some relatively easy manipulations, I'm able to solve the impulse response of the companion system. In a step 2, I'm determining age of t from yn of t and p of d, right? Because remember, p of d I haven't used at all. I kind of set it equal to 1, so I need to bring that into the picture. And I already have yn of t that I solved from these considerations here. So to do that, I start like this. Consider q of d times omega of t is equal to x of t. Where is this coming from? This is the differential equation that characterizes this companion system. Now let's take the operator p of d and operate on both of these sides. You get p of d times q of d operating on w of t is omega of t is equal to p of d operating on x of t. Okay? Now, and this is not a trivial thing, you gotta show that this is the case. It doesn't do that, but in general, these operators are commutative, right? And this comes, you can try it. Put an arbitrary function here, and then differentiate relative to q, and then differentiate the result with p, and do it the other way around, and you can see that term by term you get the same results. So it makes no difference whether you're differentiating based on q and then p, or first p and then q. Now if I change these two, I end up with q of d, p of d operating on w of t is equal to p of d operating on x of t. Now, compare this equation with this equation here. You can see the right-hand side is p of d x of t, q of d times this. Well, what has to be this? Y of t. Therefore, y of t is equal to p of d operating on w of t. But if x of t is said to be delta of t, is x of t is delta of t, then w of t is equal to what? If I go back to my companion system and I set x of t equal delta of t, what comes to the output? Yn of t, right? So if x of t is equal to delta t, this is yn of t. And then substituting that here, I get therefore, now age of t, going back to the original system, if I set x of t is equal to delta of t, then the age of t is going to be p of d operating on w of t when x of t is equal to delta of t, which is essentially p of d operating on yn of t. Okay? So my impulse response is obtained as p of d operating on w of t, which when x of t is equal to delta of t. And then here, when x of t is equal to delta of t, your w of t is essentially impulse response of the companion system. So p of d time operating on yn of t. One of the things that I kind of skip to say, yn of t may actually exist for all times, right? So yn of t is zero input response, but you actually have to say yn of t is equal to yn of, it's not, it has to have the unit step function appended to it, right? And this is, why is that? Because yn of t by its nature can exist for any t, right? I have to make sure that I turn it on at 0, not before that. Remember in the previous example, our h of t was c1 e to the minus 2t plus c2 e to the minus 3t. But I had to put times u of t to indicate that this is only valid for t greater than 0. Same here. Yn of t may have values as a function for any t. But to make sure that which yn of t I'm looking at, then I have to put y of t to make sure that I'm only looking for t greater than 0. Therefore, so summary, our h of t is given as p of d operating on y n of t plus u of t, times u of t. And then, look, this system here had m equal to 1, so it was smaller than n. So it cannot produce the delta pulse, so I have to kind of put here plus p0 times delta of t. And that's a general form of the impulse response of the system S. Now this simplifies. If m is smaller than n, so this is general. If m is smaller than n, then it can be shown that h of t is equal to b0 delta of t, and then plus p of d, now operating only on yn of t times u of t. Okay, so that's a general form of the impulse response. So let me summarize all of these in few steps, kind of like almost like an algorithm, and then we'll go to several examples illustrating how you do this particular procedure to determine the impulse response. While I have it still on board, let me just summarize before I start writing. So there are two essentially big steps and a couple of sub-steps. First big step is define a companion system and search for an impulse response of the companion system. The way how you search for an impulse response of the companion system, you're going to solve for a zero input response of a system who has differential equation given like this, and initial conditions given by this set here. This gives you a unique yn of t. You have to make sure that now yn of t proper is whatever comes out as a function here times u of t, because all of this is valid for t greater than 0. And that's the end of the first big step. In a second step, after all of this, you're going to actually determine you're not going to do any of this, right? This is just a derivation. In the second step, you're going to go straight to these two equations. And if your m is smaller than n, this becomes your impulse response. If m is larger than n, then you can use this general form here, but that's going to rarely be the case. So let me do a summary. So summary. Consider a system S is given by differential equation Q of D times Y of T is equal to P of D applied to X of T. I say times, but it's not really times. This is an operator on a function, right? So you're not multiplying, you're operating, right? So this every time you're taking this higher order derivatives. So I have divided this whole process into 3 steps. Step 1 is solve for characteristic modes of Yn of t. Yn of t is an impulse response of the companion system. So how you do that? You take q of lambda equal to 0. From here, you're going to get your lambda k. K goes 1 and so on. In the most simple case, you're going to get n distinct values, but in a general case, you may get duplicate roots or complex roots or whatever may be the case. And then you're going to say Yn of t is equal to your characteristic modes. In a very same way that we did last time when we looked at the zero input response. This step is identical to that step. You're going to end up with a whole bunch of n, actually, coefficients that you need to determine, right? Where n is the order of the equation. Now, step 2 is going to be determine the constants or the coefficients of Yn of t using following initial conditions. You're going to say Yn of 0 is equal to Yn first derivative at 0 is equal to Yn n minus second derivative at 0 is equal to 0, and your Yn n minus first derivative at 0 has to be equal to 1. So this gives you exactly, see, n minus 1 upstairs and additional 1 downstairs. So it gives you exactly n initial conditions. You have n constants here and initial conditions you should be able to solve. And then step 3 is the final step. Determine age of t using the following equations. If, and I have 2 conditions here, m is greater than n, then you have to go to a more general form. Age of t is equal to b0, delta of t, plus p of d operating on yn of t times u of t, right? And why is this important? Because this will give you a whole bunch of additional impulses once you start differentiating u of t. Because u of t, derivative of u of t is delta, gives you delta at the origin. And then for n smaller than n, age of t is going to be b0, delta of t plus p of d times operating on yn of t, but that now multiplying u of t. And this is much simpler because you don't have any deltas. This one does not have a delta pulse because remember it is the companion system at b0 equal to 0, right? So it has only it has a impulse response that consists only of characteristic modes. So these are 3 steps. You know, algorithm you just execute and you get an impulse response. Easy as 1, 2, 3. So let's use some examples. This is example the same as your example 2.4 in the textbook. Here's the system we have: d squared plus 3d plus 2 y of t is equal to d x of t. So let's see how we implement it. Step 1, and this is this step here. I'm going to determine the characteristic value of the impulse response of the companion system. So I'm going to say q of lambda is equal to 0. In our case, lambda squared plus 3 lambda plus 2, which is lambda plus 2 times lambda plus 1 has to be equal to 0. And I solve for them. Lambda 1 is minus 2, lambda 2 is minus 1. So I get with my general form of yn of t to be c1 e to the minus t plus c2 e to the minus 2t. And important times u of t, right? Because this is valid only for t greater than 0. See, I say important, but I don't put it in the notes. Make sure that this is there. It's u of t, right? Because it's only valid for t greater than 0, and these functions, they exist for every t. So that's the end of the step 1. In step 2, we have to solve for C1 and C2. We're going to solve for them by looking at the proper initial conditions. And initial conditions are given over there. So let's say, let's do step 2 now. We're going to say yn of 0 is equal to 0. Yn prime of 0 has to be equal to 1. This yn of 0 is equal to 0 is this guy. N minus 1, n in this case is equal to 2. So the first derivative has to be equal to 1. Now if you look at these two conditions and this one, when I substitute, I end up that C1 plus C2 is equal to 0. And then minus C1 minus 2C2 is equal to 1. So if I add them together, C1 and minus C1 cancel, so minus C2 is equal to 1. So C2 is equal to minus 1, and C1 therefore has to be equal to 1. And my yn of t is e to the minus t minus e to the minus 2t times u of t. So that's the impulse response of the companion system. In step 3, I'm going to determine the impulse response h of t. I'm going to be using this equation because n is smaller than n. How do I see? n is equal to 1, n is equal to 2. So all I need to do is, I'm going to say 0 times delta of t, y0, because b0 here, the coefficient with d squared is equal to 0. And then I have to plus d operating on yn of t times u of t. That means I need to take the derivative of this one times u of t. And derivative is minus e to the minus t plus 2 e to the minus 2t times u of t. So that's an impulse response of this system. Any questions? Let me go through a couple of more examples so that one of them, for example, that has an impulse at the origin. So this is a exercise. I think these are not examples, these are exercises. They're just given at the bottom without any solution. So that's why I'm solving over them, so that you can see how to solve and have an extra set of problems to practice. So this is exercise 2.4. Now here I have a system, and this was a part, I guess part A in there. This is exercise. And this was a part B problem. Here I have d plus 2. Sorry. Just a second. This part, this is d plus 2 y of t is equal to 3b plus 5 x of t. Now, how large is n in this case? Is equal to 1. How large is m? Equal to 1. What do I know about this impulse response? It's going to have a delta pulse at the origin. And what is the area under the delta pulse? It's going to be 3 delta plus the plus my all my natural responses or characteristic modes. So in step 1, I'm solving for characteristic modes of yn of t. So here I say q of lambda is equal to lambda plus 2 is equal to 0. Solution lambda equal to minus 2. And yn of t has a general form constant, what do I call c1 e to the minus 2t times u of t. That's my impulse response of the companion system. Step 2, I solve for initial conditions. Since here the n is equal to 1, the zeroth derivative, yn of 0, has to be equal to 1. Like the previous derivative has to be equal to 1, and all the others are equal to 0. So from here, I get c1 has to be equal to 1. Why? When I substitute 1 here, e to the 0. When I substitute equals 0, I get c1, so that has to be equal to 1, so c1 is equal to 1. And therefore, my impulse response of the companion system is e to the minus 2t times u of t. So that's the impulse response of the companion system. And then step 3. Now, I know that h of t is going to be p0 delta of t plus, since n is equal to n, so I can say p of d operating on yn of t times u of t. In our case here, b0 is 3 delta of t, and then plus p of d is this guy here, so 3d plus 5 operating on e to the minus 2t, and then everything times u of t. So let's take the derivatives. This becomes 3 times delta of t plus derivative of this is minus 2, so it's minus 6 e to the minus 2t, and then plus 5 e to the minus 2t, let me see here, plus minus times u of t. All right, how did I determine this? Derivative e to the minus 2t is minus 2 e to the minus 2t, times 3 is minus 6 e to the minus 2t, 5 e to the minus 2t is this. So when I add them together, this becomes 3 delta of t minus e to the minus 2t times u of t. So that's the impulse response in this case. And this is the case where n is equal to n. And then let's take a look at, I guess here yet another one. I'm going to skip this one. Just leave it in your notes. And maybe I'll skip both of them. You have them in your notes, it's just more exercise. But I didn't deliberately because they're not solved in your book, so you can go here and follow the solution. But the steps are really, really simple. Let me repeat them again. In the first one, you solve your characteristic polynomial, just like you did for a zero input response. Then when you solve that, you form your impulse response of the companion system. It will have n constants that you need to solve for. You're going to solve these n constants by applying these initial conditions. You have to be careful for these initial conditions. Everything is 0 up to the n minus second derivative, but the n minus first derivative is equal to 1. If this n minus first becomes 0, then that takes the precedence of this one, right? You follow what I'm saying? Like this can work only if n is greater than 2, right? But if n is smaller than 2, then actually n is greater than n is greater than 1, right? Because of this. If n is equal to 1, then this becomes your zero derivative. So yn of 0 ends up being equal to 1, just like I did in this case here. Once you do this, you're going to end up with an exact expression for yn of t, and then you're going to determine your impulse response from the original system by taking essentially the derivative of this impulse response of your companion system. Why does this work? Is it obvious? Why is this true? Why does this have to work? Remember my first assertion when I said, well, this system S0 is the same as S, except S is taking the derivatives of the input before it presented to the system, right? You can take the S0 and split it into two systems. Split it into its companion system that it's fed by the derivatives of the x of t, right? P of t, x of t. So what this is saying, if your input is the derivative of your input to the companion system, then the impulse response of your system has to be a derivative of the impulse response of the companion system, because all of these are linear operators, right? If I feed x of t into this system and it produces y of t, and then I have another system that takes the derivative before it presents to but it's the same characteristic polynomial, then the outputs of this system have to be derivatives of the output of this one, right? Because all around they're linear transforms. There's a little bit of quirkiness with these B0s and deltas and what happens when you have a direct path between input and output, because that's what these extra terms are. But in most cases, these guys are going to disappear anyway, because n is going to be smaller than n. And in that case, you end up with essentially this, saying if I'm differentiating input and I'm getting if I'm taking an impulse response of the companion system, and this is yn of t, and instead of presenting x of t to the companion system, I present derivatives of x of t, then my output needs to be derivative of my impulse response for the companion system. That's what all of this kind of boils down to, right? Intuitively. Now mathematically, you have to be careful because there are some other little quirkiness that we need to take care of. All right, so let's look at where do we go from here. Now remember, what our goal is to be able to feed x of t. Go ahead.
The general form of P of D is the B naught is in the first term?
First term, the one with the highest.
The Bm is the
highest
last term. Bm is the last term.
Bn, or n minus n. This is how we had it. Let me just, yeah, because it's different from book to book, right? So this is why you need to be careful. When I switched to this book, I had a lot of trouble with exactly this. This is the long form, short form, P of D, Y of T is, see, Q of D is P of D times X of T. Q of D starts like this. It is, you think of it A0, but normalizing it, we make A0 always equal to 1 by taking the gain outside, right? So then you have 1 times d to the n, then plus A1 d to the n minus 1, plus and so on, plus an d to the 0, right? Or just an. And this is Q of D. P of D is B0 times d to the n plus B1 d to the n minus 1 plus and so on plus Bn. So they're kind of the same format. Most of the time, you're actually not going to have few of these terms.
D to the n or n?
D to the, well, you're not going to have most of these terms. So then you're going to start by Bm d to the n minus m plus Bn. Sorry, what did you say? B n minus m, right? So that's what you're going to have most of the time, right? Where then m is going to be the order. If n is equal to 0, then all you got is this, right? If n is equal to 1, then you have two terms. If n is equal to n, then you go all the way to this, right? So that's how the this book that we use adopts to write these polynomials. Now, so let me go back to big picture. We have now determined the response of, we have determined two things. First, we've determined what happens at the output of the linear system if it's left without any excitation, but it has some initial conditions. We can solve that. That's what we did last time. Now we said, well, we can determine also what happens to the linear system if I have a special kind of excitation. I have a delta pulse presented to the linear system. So to get everything closed, we need to now say, okay, well, let's generalize this and see if we can predict what happens if I don't restrict what is it that I'm presenting. I'm not presenting delta, I'm presenting function x of t. So let's see if we can get there. To do that, there is one thing that we need to do beforehand, and this is a system response to delayed input. Okay? So here's the settings. I have x of t is delta of t. Then what is y of t? Y of t is equal to h of t. Let's say x1 of t, y1 of t. x1 of t is equal to delta of t minus some capital T. What is y2 of t? It's going to be h of t minus capital T. That's coming from what? From the fact that our system is time invariant, right? And this is something that we kind of started from the very beginning. We say our system is time invariant, and therefore this is all true. Whenever I did it with the response, if I delayed the response, the output is delayed for the same amount. Okay, so now zero state response. Okay, so we are now addressing the big question here. So I have the system. This is what I know about the system. If I present delta of t, I'm going to get h of t. And I already did my math, so I know what h of t is for this delta of t. The question here is, if x of t is presented here, what is y of t? Okay? And also, the following, so this is the first thing. The second thing is, system is in zero state. What does this mean? This means that the system had no energy before t equals 0, which we can summarize in a set of initial conditions, y 0, 0, y first derivative of 0, all the way to the y nth derivative of 0 is equal to 0. And also, the third thing that is known is that differential equation P of Q of d times y of t is equal to P of d times x of t. So these are all known. Okay. Now let's work a little bit on x of t. We can see x of t in a special light that will make the solution of this really, really elegant. Here's my x of t in general case, some function of time. Now, here's what I'm going to do. I'm going to imagine increments of time, and let's make them delta t, for which I can define a function that kind of looks like this, right? This stepwise approximation of x of t. So I'm going to define x hat of t that will be something like this. Sum over n, x of n delta t times pulse of t minus delta t. What is this p of delta t? The easiest thing is to draw it. So this p of t minus delta t is the pulse that sits at the origin. Its width is delta t, and its height is 1. So that's a pulse p of t. When I do this, I delay it by n delta t, and then I scale it by the value of the function in this. This is n delta t. Right? So I'm saying, in order to build this x of t, I'm going to actually scale these, put these square pulses right after the other. The value of the pulse is the middle here, and I'm making a little bit of error here, I'm making a little bit of error there. But you can intuitively see that as delta t approaches 0, these two come closer and closer, right? Because there's essentially you're converging x hat of t converges to x of t. Now let's play a little bit with x hat of t. X hat of t, I can say now sum over n, and I can say x of n delta t divided by delta t p of t minus n delta t times delta. All right? What did I do? Nothing smart. I just multiply and divide it by delta t. Now, it's easy to see that limit when as I should say as delta t goes to 0, x hat of t goes to x of t. Intuitively, that's easy to understand. You make this delta t smaller and smaller. Pretty soon you need a magnifying glass to tell that there is an approximation, right? Because it's pretty much writing the exactly x s of t. So let's do this. Limit when delta t goes to 0, x hat of t is going to be now limit when delta t goes to 0, and then sum over n, x of n delta t, and then I'm going to say p of t minus n delta t divided by delta t times delta t. Now, there is some strict math that we can spend some time, but there's no need. We've seen this before, and it's easy to recognize what does this become. As delta t goes to 0, what does n delta t go to? Well, you have something that these increments become smaller and smaller, but the thing is you have infinitely many of them, right? Because this n becomes larger and larger. So you're kind of walking on the real axis, but instead of making these kind of steps, you're making steps that are smaller and smaller, right? And eventually, what is it that you're doing? You're sweeping the entire axis by making infinitesimally small steps, but making infinitely many of them. So you're going through every single point. So this becomes a continuous variable. Let's call it a tau. Now this guy, x of n delta t, becomes x of tau, right? It becomes the x at some continuous point tau. Now this guy we've seen before. This is the pulse that becomes narrower and narrower, but whose magnitude becomes larger and larger, right? Let's assume delta t is equal to 1. That is the pulse of width 1 with a height 1. But if I make delta t goes to 1/2, then the width of this 1/2, but this is divided by 1/2, so it goes 2 times 1/2. What is the area under the curve? Still 1. And then as delta t goes to infinity, what does this become? Becomes a delta, the impulse, t minus tau, right? So this whole thing, phi of t minus delta t divided by delta t becomes delta of t minus tau, right? Because it grows infinitely in the magnitude. It is center of n delta t, which becomes continuous variable tau. So this is delta, and then this delta t is so small, I'm going to call it d tau, right? So to make long story short, limit x hat of t, which is x of t, is going to be integral when tau goes from minus infinity, x of tau, delta of t minus tau, d tau. Well, you say, this is a shifting property of the delta. But that's a kind of another way to see it. The better way to see this is I'm saying delta now is seen as a whole bunch of this, not delta, x of t is seen as a whole bunch of impulses that are hitting the system, right? One after the other, right? So this is how I see my input. Now if I look at, well, what happens at the output? Well, every one of these delta pulses, since delta of t produces h of t, and delta of t minus tau produces h of t minus tau, according to the delay property over there, then I obtain that y of t is equal to integral, when tau goes from minus infinity plus infinity, x of tau, but instead of this delta that was here as the input, every delta produces output h. So it's going to be h of t minus tau delta tau. Right? So, and this is our good old friend. How do we call this? Convolution, right? So this is a convolution integral. So equation is well-known and highly respected convolution. In your book, there's a guy that holds the, you see the banner says, make love, not convolution, right? So the problem with this is, I think, when it's taught for the first time, what they teach you is, they say, oh, okay, what is convolution? And then they give you this recipe. You flip, shift, and all of this stuff, right? And they're actually kind of doing you disservice, because they're teaching you methodology, how you compute it, instead of explaining what it is, right? And then it ends up being that you end up thinking that something is flipping and shifting. Nothing is flipping and shifting here, right? This is just the way how you calculate. What is happening here is our linear system reacts to the impulses that are being fed to the input. Now, my x of t can be decomposed this whole bunch of impulses, and now therefore my y of t is seen as a whole bunch of impulse responses coming one after the other, right? So x of t is this, and y of t is kind of responding to each one of these impulses. So just like your x of t is an impulse that it's some of the impulses across all taus, that have magnitude x of tau d tau, and they are shifted to delta of t minus tau, your output is going to be some impulse responses that have magnitude x of tau d tau times the impulse response. And then you have to sum all of them across all possible counts. Okay? So that's, we kind of reached the end of this part of the journey. We have two things. We have a response of the system to the non-zero initial conditions. That's what we did last time. What we did today is we developed the response of the system to a non-zero input. The total response, because the system is linear, is going to be sum of it. Okay, here are the list of problems that exercise this. 2.3, 1, 2, 3, and 4. And I always advise you, there's a M22, which is an M file. Please review that M file as well. It gives you the code that helps you, plot some of these things, play with them, and kind of see this on the computer screen.